When you have multiple forces on an object, the net force is going to be a combination of all these forces, their vectors all added together, and this is going to determine acceleration. Like if you have both gravitational force and normal force acting on an object, which is just sitting on a surface like this, and they're the same magnitude and going in opposite directions, the net force will just be 0 and it will be standing still. If you have arrows of different magnitudes or in different directions, then it gets a little bit more complicated. So I'll do an example problem from the physics test to show this. So if we have an inclined plane and a pulley with two objects connected to it like this, it's saying that a block of mass m is connected by a string to a sphere of mass m, and the block is on a frictionless plane inclined at an angle of 30 degrees as shown in the figure above. The string passes over a pulley of negligible mass and friction, and the sphere hangs freely. Which of the following is true if the block is accelerating down the incline? So if we draw a free body diagram of this block, so we have our block of mass m, m1, oh, I messed up. Okay, it's on an inclined surface. We know that the force of gravity is acting on it straight downward, and the normal force is acting on it from perpendicular to this surface, and then the force of tension is acting on it parallel to the surface, like this. And we know that it's accelerating downward, so we're gonna use a plane or coordinates like this. These are gonna be our axes that we're gonna calculate total force on. This. So we already know that the total force in the y-axis is going to be 0 because it's on this plane, and yeah, it's sliding down, but it's not like going through the plane or levitating above the plane. So that's going to be 0, and we can use that to calculate the normal force. The angle goes into play with this, so we can draw the components of each force with those axes. So tension is going to stay the same. For gravity, part of it is going to be going, so tension stays the same. And this is basically our theta right here. So the part in the y-axis is going to be mg sine, or no, cosine, sorry, cosine theta, and the part in the x-axis is going to be mg sine theta. And then as far as the normal force goes, that's just equal to mg cosine theta, but that doesn't really matter here. I'll draw it in anyways. So this is our new free body diagram with all the force components rather than the actual forces. So if this is sliding down, then we know that mg sine theta is going to be greater than the force of the tension, right? So now let's calculate what the force of the tension is, right? So this can be done with a free body diagram of mass 2, right? So this is our free body diagram here, right? Because it's just suspended. And we know that if M1 is sliding down, that this is going upwards. So we know that tension here is greater than M2G. So we know that from there that because of those two, we know that M1G sine theta also has to be greater than M2G because M1G sine theta is greater than tension, and then tension is greater than M2G, so by extension that has to be true. And I wrote it down right here. And then we can cancel out our G's, and we're left with M1 sine theta is greater than M2. And in this case our theta is 30, and we can just sub that in the equation, and that is an option for our multiple choice, option E. So that's the answer. And that's what has to be true in order for block M1 to be sliding down this incline.